Welcome to a lesson with Dr. Powell. We're going to look at some ways that we can remember our log properties and how they work. Just remember what a logarithm is. It's an exponent extractor. Let's work with log base 2. So, since there's an exponent extractor, properties of this are going to be the same as looking at what's going on in the exponents. What's happening? For instance, what if we had log base 2 of something like a times b? Now let's think about a as being 2 to something, whatever it is, and b as being 2 to maybe something else. In fact, maybe we'll just say x and y for now, x and y. Now, what's happening in the exponents when we multiply these two things? Well, if we multiply these two things and they have the same base, then the exponents add. Remember what x is? It's the exponent to get to a. And y is the exponent to get to b. So what we're going to do is we're going to add the exponent to get to a, which we can actually notate as log base 2 of a. That's the exponent to get to a, and add it to the exponent to get to b. And that addition of exponents will be the exponent to get to a times b. So really, it's just a statement of exponents. The exponent that 2 needs to get to a plus the exponent that 2 needs to get to b is equal to the exponent that 2 needs to get to a get to a times b, because exponents add across. So this statement is nothing more, this property is nothing more than just thinking about what's going on in exponents and thinking about each logarithm as an exponent itself, the exponent to get to whatever's inside of it. Then what about this one, log base 2 of a over b? Now, when you divide and you have the same base, remember, exponents subtract. So you can naturally think it's going to be, so the exponent to get to this is going to be the exponent to get to a minus the exponent to get to b. And the exponent to get to a is written as log base 2 of a. And then you subtract off the exponent that you need to get to b. And so you have these two properties, which are fundamental and very useful. We also have another one. What if we did something like log base 2 of a cubed? Now think about what this 3 is doing. This 3 is an exponent, and whatever a is, let's suppose a is something like 2 to the x, and raising it to the third power. So the exponent to get to a is x. And what are we doing with it to get the exponent to get to a cubed? Well, we're multiplying it. You see that? That's across, because what does this mean? I mean, let's just think of an example. If x happens to be 4, then what we're doing is we're saying 2 to the 4th, 2 to the 4th, 2 to the 4th, when we do 2 to the 4th cubed, and then we end up getting 4 plus 4 plus 4, which is the same as 4 times 3, meaning that we get multiplication of exponents in this case. So since the exponent to get to a is now multiplied by 3, we can actually notate that simply as 3 times the exponent to get to a. In other words, we imagine this as just heading down. I mean, you can take all these things for granted and just consider them as rules, or you can think intuitively and remember what is actually happening, because it all does make sense and it all works in a very nice way. Those are 3 basic properties of logarithms. And here's another one, change of base, and this will come up as we go forward. So change of base, how can we work with that? So what is that? Well, let's suppose we have log base something, like 2, that's fine, we can just keep with that. Log base 2 of something, and maybe we'll do 5. And maybe we'd like to rewrite this and see what it is using another base, like maybe 3. This is going to be equal to some expression with log base 3. How in the world can we do that? Well, let's just think what this is. This is the power that you have to raise 2 to get to 5. So let's think about that. This x is going to be equal to this right here. So to get x to be in terms of log and another base, why don't we just look at this equation here and use log base 3 to extract exponents. So let's suppose we have log base 3, 2 to the x is equal to log base 3 of 5. I just applied log base 3 to both sides. Now notice we have a nice property of logarithms. We have an exponent here, and it's an exponent land. It comes out and multiplies to the exponent that we have to get to 2. So this just naturally becomes x times the log base 3 of 2 is equal to log base 3 of 5. This tells us that x is equal to log base 3 of 5 divided by log base 3 of 2. That is exactly what log base 2 of 5 is in terms of log base 3. Notice what we've done. We've taken log base 2 of 5 and we simply just rewrote as log base 3 of 5. But the trade-off was to divide by log base 3 again, but of 2. Notice we have log base 3, log base 3. What goes on the top is on the top right here. It's higher than the 2. What goes on the bottom is what's down below. So in general, if we want to change a base, and let's change it to base 10 this time. So let's suppose we have log base 5 of 7. How would we write this in terms of log base 10? On a calculator, log base 10 keys and log base E keys are where E is a number that we can use as a base, and 10 are often available. So it's nice to be able to convert into those. So simply just choose what we want to use. Let's use base 10. So let's use log. And when it's base 10, we can ignore writing a 10, just write log. We have a log on the top, a log on the bottom, with the same base on top and bottom. And what goes up here is the higher number, which is natural. What goes down here is a lower number. So we have 7, 5. And that's the way that we can rewrite a logarithm in one base into another. And the beauty of this is this equation works no matter what base we use. We could replace log base 10 with 2 or pi or 6 or anything we like right here. And it would work just fine as long as it's a positive number. So for instance, this is also equal to, so ln is another way of writing log base E, where E is about 2.7 something or other. And so we could rewrite this ln of 7 over ln of 5. This is a nice property to use and have handy. Thanks for watching.